Welcome to the e-Pathshala lecture series on computer science for postgraduate students. We are into the 20th module of the subject computer graphics and visualization. In this lecture series for the subject computer graphics and visualization, in the previous module, that is the 19th module, we talked about rendering, an important technique which brings what is called which imitates the real world objects as closely as possible. So with advanced rendering techniques like ray tracing, we were able to achieve the visual realism that had been the ultimate goal of 3D world, or the 3D virtual world that we have created. In this module, we will talk about animation, which is the animation is like, say, where computer graphics without animation is something which we cannot afford to lose. So animation is an important concept or important topic which we should discuss as part of this series, as part of this subject. So this is the 20th module discussing about, we will be discussing about the concepts of animation. Okay. Let us get into the objectives. The objective is to understand the basic terminology of animation, to understand the principles behind the techniques of animation. So there are many techniques of animation. So as soon as we hear the word animation, something immediately pops into our mind, or pops up into our minds. Animation is like, say, the cartoon shows, the kinds of 3D animations, the kinds of simulations, and so on and so forth. So all that is true, and there is a lot of techniques behind the very word animation. So animation is something that is fully created using electronic means, that is like a computer. So animation is fully done and created and designed, created and done fully using electronic means or the computers. Now some of the keywords here are tweening, morphing, kinematics, and many more. So let us understand the very definition of animation. So animation is something that is like, say, a series of frames that are constantly changing before us, or like, say, in simple terms, any time sequence of visual changes in a scene can be considered as an animation. So animation is a series of frames that are constantly changed with a frame rate. So the important phrase there is the frame rate. So the frame rate decides how many frames should be there in a second, so that the animation is much smoother and it is valid for the chosen animation. What are the visual changes here? So what do we mean by visual changes here? So anything that changes before our eyes is a visual change. So the change can be in terms of shape, the change can be in terms of size, the change can be in terms of color, in terms of texture, in terms of many other properties of the objects. So visual changes to any of these properties of objects and many more here listed can be considered as animation. So now you can wonder, say, these changes give us a feeling that something is happening before us, or something is getting animated. The characters undergo these changes so that we feel that they are in an animation. So the various versions of animation that people have been trying over years, people have been using over years, are 2D, 2.5D, 3D, and 4D. What is 2D? 2D animation is something where in the olden days, when there was nothing like 3D or the 3D animation software like Max and Maya, when nothing of that sort were available, then it was only 2D. So 2D is simply basic plain images, and they are constantly changed, and where the 2D version lacks a kind of depth and a kind of feeling that it is made up of real world objects. So we will feel a kind of, say, we will immediately come to know that it is a pure cartoon character. In the case of 2.5D, the half there is nothing. See, don't worry about the half, seeing half there. Half is an addition to 2D. The half is giving a feeling to the users of 2D, or the viewers of 2D, that it is 3D. So giving a 3D feeling by using 2D is 2.5D. Giving a 3D like feeling in 2D is 2.5D. So by adding shadows, or by adding some kind of what is called extra features, by giving a direction to them and so on and so forth, we give them a feeling, we give the viewers a feeling that it is 3D. Okay. So that is 2.5D. The next kind of animation is 3D. So 3D is pure, as we discussed earlier, using using 3D Studio Max or Maya like software, like Blender like software. So we can create 3D objects and we can create views and we can do all that. So that is purely 3D. We get the feel for the depth and we get the feel for the real like objects. And the next thing is 4D. So what is 4D? We know there are only 3 dimensions for real world objects and even the artificially created objects. The 4D is an addition, so we add something like a feel for touch, and we will have extra gadgets around us, or we have some kind of changes to the physical world where we are sitting, and we might wear some kind of gloves, we might wear some kind of electronic gloves, kind of headset, and we feel that we are in another world where we can smell, we can touch, and if these kinds of extra attributes are added to the 3D, we say that it is 4D. Okay. So animation can be in either of these forms. Before an animation is done, or before something is visualized, we create, or we can call them some kind of these master animators, or people who are like the core people, the industry. So they will be creating what is called a storyboard. The storyboard is a graphical layout of the entire animation sequence. So they will be drawing the characters, or they will be positioning them, or they will be knowing, so like say when what should happen. They will be doing all that on a paper, or maybe it can be in the form of electronic means, or it can be in the form of a slide. It can be, but it is fundamentally a pre-step. It's a pre-step, precursor for animation. Okay, it's a storyboard. So once the storyboard is done, we will get a feel for how the animation is going to be, how it will be visualized at the end. So it's a graphical layout of the actual animation. Once that is done, the objects are defined, their properties are defined, then we will be using a technique like say a keyframe technique or a keyframe animation technique, where there are keyframes which are important frames. The keyframe means an important frame. So the master animators will be defining the keyframes, say keyframe 1, and after say after a little duration, time duration, they will be giving another keyframe, or they will be defining another keyframe. So the master animators will be defining the keyframes where there is a considerable change or a noticeable change in the course of animation. So the keyframes are defined by the master animators, and the in between frames are done by the junior animators, or you can say they are the subordinates, and now this place is filled up by the machines. So the machines or the computers are they interpolate the in between frames of 2 keyframes. Okay, they interpolate the various possible other frames depending on the frame rates chosen. So let us understand what is frame rate. Okay, so the frame rate is the number of frames per second. As we know, for animation we can still go to a number, say 12 frames per second, 15 frames per second is still acceptable. It depends on how much action we would want in the animation. It depends on the frame rate, depends on how much action we want in the animation. So there is a lot of action, lot of changes are to be there, then we will increase the frame rate. Otherwise we can afford to have lower frame rates. The higher the frame rates, the higher is the processing capability required, and vice versa. And the video, if we say video, the real life objects are what are captured in the video, which is 24 frames per second or 30 frames per second, and even if we can go higher. Monitors have 60 frames per second is the frame rate defined, the refresh rate for the monitors, and animation we can still be happy with 12, 15 and so on. So some of the popular techniques of animation which are listed here on your screen, but this is not the exhaustive version. There are many more recent techniques. We will be discussing some of them here in this module. The techniques of animation. So the olden day animation techniques, the very beginning techniques, the initial techniques of animation with the frame by frame animation. The keyframe. Let us know the list first, and then we will go into details of each of these techniques. The frame by frame animation, keyframe animation, onion skinning, rotoscoping, squash and stretch, secondary action, morphing, motion capture, kinematics, and there can be a big list. So added to this, there are many new techniques which are not discussed here, so but some of the standard techniques are given here. Let us see each of them in detail. The frame by frame animation is the olden day technique used for animation, where each frame is individually edited, individually composed, and they are all played at a faster rate, so that a character walking, if we want to show that, so if you want to have 10 frames, if you want to do it in 8 frames or 10 frames, each and every frame you should manually create, edit, and between 2 frames there will be hardly any change. So each thing you should do it manually and individually. You can also use machines for this, or computers for this, where you can place each frame along a timeline, and then you can quickly play them back, so that you will have a feel that there is the character is actually walking. So again, the important thing is how many number of frames, that is frame rate, is what is important. Based on that, the number of frames are actually decided, or the number of frames in which the content should change will be decided. Okay. So the first thing, as we saw, is frame by frame animation, and the next thing is the most popular and the most used animation technique, which is the keyframe animation, where keyframes here are the important frames. Important frames are where the frames where the content has a considerable change. Okay, the changes in the animation are considerable. Okay, between 2 frames the changes may be gradual, but exactly at the keyframes, that is, if we compare keyframe 1 and keyframe 2, there will be a big difference. If we compare keyframe 2 and keyframe 3, there will be a big difference. So depending on the kind of, that is, how you design the animation, how you want the animation to happen. If you want sudden change to the character's properties, you can give a keyframe with less interval, with less spacing between the previous keyframe and the current keyframe. If you want a gradual change, you can keep keyframes much apart, okay, along the timeline. So once the keyframes are defined, as you can see in the figures here, the first keyframe has got a ball positioned here, second keyframe ball above, and third keyframe ball here in the to the right. And now you can give it to the software, like any animation software. It automatically tweens. The word tweening means interpolating the in between frames, or in between 2 keyframes. Now the word tweening has that meaning. The number of in betweens is decided by the frame rates as required. Now the kind of interpolation or the tweening depends on how you want the object to go, or what kind of path you want the object to. So if you can do it in linear interpolation, you can do a kind of what is called a curved kind of interpolation. You can decide on the shape of interpolation or the shape of tweening, okay, for the in-betweens. So how you tween the in-betweens, or how you interpolate the in-betweens, depends on how the path should look like. Okay. So another technique used for animation is the squash and stretch. You can imagine the cartoon characters, where a cartoon character like say Tom and Jerry, or like say your favorite characters, which keep running constantly one behind the other. So once they hit an object or a firm wall, like what happens is the Tom or Jerry, they bombard, or they bang the wall, and the shape suddenly changes. And so the shapes, what is called the squash and stretch, is like, squash is like their shapes, the shapes get squeezed, and the stretch is like their shapes elongate, as you can see here in the. So you can use such techniques for animations. Okay. Some of the other techniques that are popular in the animation world are the morphing, which has been quite popular, and we convert one object into the other. But this is not just as simple as converting one thing to other. Anything to anything is not possible. So you cannot convert any random thing to any other random thing. There is a condition. So there is some specific condition is to be satisfied by the 2 objects participating in morphing technique. For example, you have got a initial object, you have got a target object. So they should agree on some condition. What is that condition? The condition is that the number of vertices with which the initial object is made up of should be exactly the same as that of the number of vertices with which the final object is made up of. Again, let me repeat, for morphing animation to happen, the two objects participating in the morphing technique should agree on some condition or should satisfy a condition. What is that condition? The number of vertices with which this initial object is made up of should be exactly the same as the number of vertices with which the final object is made up of, so that you can perform a morphing. So, we will be mapping these vertices, and according to the shapes we will be changing it. As you can see here, a person is changed to another person, an object like a banana is changed to some other object like an orange or something. Okay. So, that is where morphing technique is so useful. So, here we can perform this morphing technique, we can understand this better by looking at thing here, using what is called linear interpolation. Imagine you got an object with two vertices, so an object is made up of two vertices. Now you want the object to have three vertices. Okay. Initially there were only two vertices, now the final object is made up of three vertices. Now how do we interpolate from two vertices to three vertices? How do we map? So we cannot map as far as morphing technique is concerned, the constraint is concerned, the number of vertices should be exactly the same. Now because they are not the same, we will add an extra vertex to the initial object. So that is the extra vertex added. Okay. You can look at the extra vertex added, and the extra vertex is now mapped, is now changed, and accordingly we perform a linear interpolation so that we see the final shape with the three vertices, as you can see here. For this we have a technique, an algorithm, a set of steps, we will see that later. So another simple thing which you can better understand the technique of animation is shown here. You have got a triangle, the triangle is to be changed to a rectangle. Now triangle has got three vertices, the rectangle has got four vertices. Now how do we map between the two is we add an extra vertex and to the initial shape, and we map the, now there are four vertices as you can say. So this extra vertex is added on any one of the edges of the sides of the initial shape. As you can see here, it is added to one of the edges of the initial shape, so that they can be conveniently mapped, so that the shape has now four vertices which can be conveniently mapped to the four vertices of the rectangle, and you can perform a linear interpolation. Okay. So the technique used is, the algorithm used is shown here. If we want to, so you can also equate edges or you can also equate vertices. You can follow either method while performing morphing. So for the initial shape and the final shape, you can either compare the number of vertices and you can compensate for the number of vertices, or you can compare the number of edges and you can compensate for the number of edges. This method takes edges into account. Let Lk be the, and Lk plus 1 be the number of edges or the line segments, you can call number of edges of the two consecutive frames. K is the initial keyframe, K plus 1 is the next keyframe. Define L max, maximum is the number of edges in the initial shape and the final shape, the maximum. L min is the number of edges among the two keyframes. So let us define NE. NE is the number of edges of keyframe min. So okay, number of edges which is L max mod L min. So we are performing a modulus operation here, L max mod L min, and that value is assigned to NE. What is NE? Number of edges. NS is number of sections. NS is number of sections. So which is typecasted to integer, and it is a division between L max and L min. So it is actually what is called integer version of this division, because the division can give a float value or a fractional value. We are converting that into, typecasting that into an integer. Now see here an example. If Lk is 15 and Lk plus 1 is equal to 11, we divide the four lines. You can take the vice versa, because initial keyframe should be having less number of edges and the final keyframe should be having more. We divide four lines of keyframe k plus 1 into two sections each. As per this, max is 15, min is 11. So we divide four lines of keyframe k plus 1 into two sections each. Okay, when once we make them into 2 sections each, now we have got 4. So, okay, the difference is 4, that is why. The remaining lines of keyframe k plus 1 are intact. So, what you can do is take 2 edges of one of the keyframes which has the less number of keyframes, less number of edges, the keyframe that has got less number of edges, and now you divide 2 of the edges into 2 parts each. So, we get 4. So, now they are now matching, they have an equal number of edges for each other for the first and the last keyframe. Similarly, you can use vertices, that Vk and Vk plus 1 be the number of vertices for the kth and the k plus 1th keyframe, and similarly you can define Vmax and Vmin. Maximum is the higher number of vertices, minimum is the lower number of vertices. NLS is the number of line sections, NP is the number of points. So, we have done a similar thing here, but because this is vertices and remember the previous one was edges, either thing you can try. If Vk is equal to 3 and Vk plus 1 is equal to 4, that is there are 3 vertices in the first, you can imagine triangle, you can imagine rectangle, number of line sections is equal to NP is equal to 1. So, because the difference is 1, so add 1 point to one edge of keyframe k, because keyframe k has lesser number of vertices, add one extra vertex to one edge of keyframe k. So that as you can refer to the previous slide, so where I have shown you an example of a triangle converting that to rectangle, that is what is explained here. Okay. Now, how do we simulate accelerations? So, linear interpolation is perfect. How do we simulate accelerations? Acceleration is what, or deceleration. There is a sudden change in the velocity, there is a change in velocity, suddenly something is running with much speed, suddenly something has come to a standstill. So, there is a lot of change in the speed, what is acceleration. So, how do we switch to speeds and how do we imitate this acceleration and deceleration for characters? Or we can try these trigonometric functions, and where the initial differences are less here, but suddenly there is a change, and with passage of time it is like there is a lot of movement. Okay. So, there is slow initial movement, there is slow initial movement, and later it is very high. So, that is we can keep distances between the various frames in such a way that we can simulate the acceleration and deceleration. The spacing is adjusted according to the requirements. Okay. Now, the deceleration as we discussed before, so you can perform similar such spacing, you can vary the spacing between various frames or important frames, so that you can simulate acceleration and decelerations. Okay. So, the same thing is explained here, and you can also use curves, or you can also use paths, which is path based animation. You can define a path and you can allow the object to follow that path. So, a damping motion, for example, a ball when it bounces, it slowly comes to rest. Okay. So, the bouncing ball animation can be performed by properly defining the shape of the bounce, or the kind of steps that you define, how many steps in which it should come to rest. Okay. You can define that. If you want a highly elastic ball, it might come to rest after a long time. So, depending on the kind of object you are animating, you can decide on the number of steps before which the object comes to rest. Okay. So, it is a damped sine function you can try. Kinematics and dynamics is the next and the most discussed in the literature. What is kinematics? Is imitating human like movement and giving human like movement to artificially created characters. For example, how do you give a character a kind of say suppose for example, you have created in the 3D using a 3D software, you have created a human character. Now, how do you give the human character a walk or a kind of human like movement? We have got joints, we move, so we first move our leg before we bend our legs and we do all that. See, kinematics is a study of imitating human like movement, and so that is emulating human movement using artificial characters. Okay. Now, in kinematics you can talk about two things, one is forward kinematics, the other one is inverse kinematics. What is forward kinematics? You can imagine a robotic arm here, the end thing, that is this end point is called the end effector. So, it is where that is finally its position is finally decided, that is why it is called the end effector. In forward kinematics, we adjust the angles of these various joints and elbow extensions and arms such that this is positioned finally at the desired point. This is finally positioned as desired. So, by adjusting the angles here of the various joints and other things and other components, we will be finally making it point at something or position at the desired location. That is forward kinematics. As you can see here, the animator specifies the joint angles Q1 and Q2. The computer computes where the effector should be. So, the angles are given, and the angles for the various joints are given, and the software or the computer should simulate or find out or compute the end effector's position, final position. That is forward kinematics. In the case of inverse kinematics, this is exactly opposite. We position the end effector and we in turn calculate the angles for the various joints. So, angles are computed, the end effector position is given prior and the angles are computed. So, inverse kinematics is more popular than the forward kinematics. So, the reverse process that computes the joint parameters that achieve a specified position of the end effector is known as inverse kinematics. The animator specifies the end effector position while the computer finds the joint angles, the Q1 and Q2, exactly opposite of that of forward kinematics. Inverse kinematics is more popular to the forward kinematics. And as you can see, a comparison between the two, specify conditions in forward kinematics and it computes the end effector position. The opposite of that happens in inverse kinematics. It's goal directed motion. So, where we specify the position of the end effector, specify goal positions of end effectors, compute conditions required to achieve goals. Okay, so, goal is defined and what conditions should achieve that goal is to be computed. With this, we come to the end of the discussion on animation. So, we can discuss more into what is called the other techniques of animation like motion capture. In fact, motion capture is one of the popular techniques in the industry, but due to its laborious due to the requirements that are big, that is installations and laborious requirements, the motion capture is restricted, its application is restricted. People have tried motion capture and have successfully applied an artificially created character. So, the motion of a real world object and a character, real world performing objects is actually applied and taken and recorded and is applied on an artificially created character. So, let me repeat, motion capture is one of the fantastic techniques where the motion of a real world object is recorded and is exactly imitated or exactly overlapped or is exactly applied to an artificially created character. So, that the artificially created character exactly behaves as that of a real world character. So, that is where motion capture is one of the fantastic techniques for being used for animation. There may be many other techniques like rotoscoping, which we had that in the list, but I did not mention that. Rotoscoping is another technique where we can keep the background can be fixed and we can keep changing the foreground. So, that is where rotoscoping is where on a video we can perform some kind of changes. So, on a video when we perform changes, when we perform or when we put, for example, the best example for rotoscoping is as a video and there is a text at the end of the video. So, at the end of the movie you will see the scrolling text. So, video with a scrolling text is a kind of rotoscoping. Another kind of technique you can imagine is onion skinning, which we have not discussed here. Onion skinning is one of the fantastic techniques used in the Flash software. You got this onion skinning. What is onion skinning? Onion skin is, as you should know exactly where to position an object. Suppose you want an animating ball, you want a ball to be animated. What you can do is, you can for the to exactly define the previous position of the ball, you can take the onion skinned version of it and you can forget about all the previous other versions. Let me repeat, say for example, if you want to do an animation, you do not have to define all the possible positions of the ball, rather you can take onion skinned versions of the object in the previous frames, so that you can position the object in the current frame perfectly. So, you can position the object in the current frame so perfectly. That is what onion skin. So say for example in a 10th frame, it is important, it is enough that you know the previous 2 or 3 frames. You don't have to know the first frame when you are positioning the ball in the 10th frame. So that's where you can perform onion skinning. So some of these techniques are discussed here. You can explore more in the literature and the books referred. With this, we come to the end of the 20th module for the subject computer graphics and visualization. Thank you.